Hi. In this video, I want to illustrate a few key concepts related to our paper Vortex Lens, interactive vortex core line extraction using observed line integral convolution. So this is the interactive tool that we call Vortex Lens. Essentially, it shows an alternative visualization of the vector field using line integral convolution inside the lens region. Line integral convolution is a commonly used tool for the interactive exploration of 2D flow data. Although it has well-known shortcomings, it is very frequently used. With Vortex Lens, we want to address this by preserving interactivity, but at the same time offer a tool to better visualize unsteady 2D vector fields. Let me start by explaining why line integral convolution is not suitable to visualize unsteady flow fields. Here we see the visualization of a vortex using line integral convolution. In this case, it is a steady flow field. Steady means that the velocities do not change over time. When we look at a single particle, this particle traces out a circle over time. And if we looked at several particles, they would still all swirl around a common center, which coincides with the visualization using line integral convolution. Now let us look at a vector field that is unsteady. This means that the velocities change over time. We use the same vortex to illustrate this, but this time it moves from left to right. We visualize it here again with line integral convolution. If we look at the trajectory of a particle, which is the integral curve of the velocities over time, and the center of the line integral convolution, we see that they never overlap. This means that the particle is obviously not swirling around the apparent center of the visualization using line integral convolution. In the case of unsteady 2D flow visualization, it can sometimes help to visualize it in 3D, where the third dimension is time. Here we can clearly see that the particles swirl around the common center, but the center, visualized using line integral convolution, does not coincide with the center of the vortex. When we analyze flow phenomena, such as vortex structures, we are of course interested in the motion of real particles. A vortex is a pattern where all particles in a region swirl around a common center. Because these structures stay coherent over longer periods of time, they form the basis of many physical phenomena of interest. Before I go into the details of how our approach addresses the issues of line integral convolution, let me show you some more examples of how misleading conventional line integral convolution can be. Here we can see a seemingly uninteresting unsteady flow field. However, when we seed particles at the right place, we can see that they actually swirl around the common center. Here we see what appears to be a vortex, but when we look at particles close by, we see that they aren't really swirling around the common center. We are simply looking at a rigid body rotation. Particles are not swirling around the common center, and therefore it is not a vortex. We can visualize that by untwisting them with a rigid body rotation. So when we use line integral convolution, we can see vortex structures that aren't really there, and we can miss vortex structures that are actually there but can't be seen. Probably the most common case is that we visualize vortex structures slightly off-center. Despite this problem being known, line integral convolution is still one of the most common ad hoc visualization methods in 2D flow visualization, simply because it is widely available and gives a quick overview of a vector field at a single point in time. The goal of this work is to modify the existing line integral convolution method to reveal vortex structures where they actually are, and to make that part of an interactive visualization tool. Based on our earlier work, we developed a method that computes a locally optimal rigid body motion that follows structures, such as vortex structures, over time. We then take this motion and apply its inverse to the velocity field. This means that we follow coherent patterns that move over time and visualize them from the perspective of a co-moving observer. This is again best understood when looking at actual particle trajectories or path lines. Here we see the line integral convolution visualization of a vortex street that moves on a straight line. However, the vortex structures are not visible. With observed line integral convolution on the right, we can clearly see the vortex street at the right places. So how do we go from a visualization like the one on the left to a visualization like the one on the right? Basically, all we have to do is find the path of an observer that co-moves with the vortex street and transform the velocities accordingly. However, velocity transformations can be a little unintuitive. So here I want to show the geometric intuition behind our approach. Let us look again at the input flow field on the left. On top of it, we see the corresponding path lines densely seeded over the whole domain. We want to transform the path lines now, as they are seen by a co-moving observer. We start with a slowly moving observer and gradually increase the velocity. When the vortex structures appear steady in place, we have found the observer that co-moves with them. We call this visualization observed path lines, with respect to an observer that follows the vortex street. If we now take the tangent vectors of these observed path lines, we again get a velocity field. But this time, it is the observed velocity field. In computing line integral convolution on this new vector field, we get observed line integral convolution with respect to the co-moving observer. This example is simple because a single observer which co-moves with the vortex street on a straight line is sufficient to visualize the observed flow. In practice, for more complex datasets, we need a set of observers, each following one structure on a generally curved path. However, the geometric intuition for how to transform the input field stays the same. However, because each vortex structure yields a different optimal co-moving observer, we get different observed line integral convolution visualizations for each vortex structure. The co-moving observers only make sense in their local neighborhood. Therefore, we only show the results in a lens region. Let us now have a closer look at how to compute a co-moving observer for one vortex. We use the idea of finding a reference frame transformation that minimizes the time derivative of the observed vector field. Several techniques have been developed for this in earlier work. We adapted them to be computed locally and interactively. Solving for an unknown optimally co-moving observer is an inverse problem and can be addressed with an optimization algorithm. At a given input point specified by the user, we compute the optimal co-moving observer. We can think of this optimization as a search for an observer that minimizes the time derivative. Here we visualize the time derivative as a color-coded scalar field for a given observer motion. By changing the observer motion, the time derivative also changes. Our optimization finds the observer that minimizes this scalar field inside a local region. We have now found an optimal observer for a region around the user-specified point. However, this is in general not the best start point to follow a coherent structure. Therefore, we need to run a second optimization that looks at the observed velocity magnitude in the region. Here we visualize the observed velocity magnitude for a given observer motion. An optimization method now finds the minimum in this region. We iterate these two optimization methods using the proximal operators framework and ADMM. This iterative optimization approach quickly converges to a joint minimum where the observed time derivative and the observed velocity become minimal. The result is the center of a vortex structure as well as the motion of the co-moving observer. We can use this optimal observer motion to show observed line integral convolution as discussed before. However, there's something else we can do with it. Since we know that this is the motion that co-moves with a vortex, we can now advect our vortex lens in time and repeat this process. We iteratively find the best co-moving observer and advect the lens in time. With this technique, the user can lock the lens to a vortex and let the lens advect itself through time. The possibility to change between vortex lens exploration in space and vortex lens advection through time provides an intuitive and powerful novel exploration metaphor. To ensure that our approach reliably finds vortex structures and that the visualized vortex core lines are of good quality, we have compared our method to state-of-the-art vortex core line extraction methods. For more details on this part of the evaluation, I would like to refer you to the paper. For more details on the mathematical framework that is behind our observed flow visualization methods, I would like to bring to your attention our much more detailed tutorial videos and notes. Thank you for watching.